Hey there, subscribers! A big shout out to all of you. We can't thank you enough for your unwavering support. Your participation and engagement are what fuels our journey, and we can't express enough how much we appreciate you. Now, let's get down to the business of the day. Have you ever contemplated the pivotal role of quality control in various fields? Today, we're diving deep into its significance and the key terminology that helps define it. Quality control, the cornerstone of consistent and reliable products and services, is an intricate and an intriguing field. It's more than just checking the end product. It involves a scientific approach that ensures utmost excellence at every stage of production or service delivery. We'll be exploring a gamut of terms that form the very basis of this discipline: linearity, coefficient of variation, pre/post-analytical, accuracy, skewness, confidence limit, precision, mean value, normal distribution, reliability, standard deviation index, delta, OD shift, trend, and Levey-Jennings charts. Each of these terms constitute a fundamental part of the quality control puzzle, offering a unique to examine and ensure quality. Grasping these terms and their applications can equip us with the tools to create superior, more dependable products and services. Now, let's unravel these terms one at a time. To start off, we'll look at linearity and coefficient of variation. Linearity, in the realm of quality control, is a property that reveals how a change in the input of a process or system leads to a proportional change in the output. It is a characteristic inherent in systems that respond proportionally to changes, such as a weighing scale. If you put 2 pounds on the scale, it indicates 2. If you add another 2, it reads 4. That's linearity in action. The importance of linearity cannot be overstated. It ensures the accuracy of measurements across a range of values, guaranteeing that your results are not only correct at one point, but across the entire spectrum of your measurements. Moving on, let's talk about the coefficient of variation. This is a statistical measure that helps assess the reliability of measurements. It is calculated as the ratio of the standard deviation to the mean, expressed as a percentage. The lower the coefficient of variation, the more reliable your measurements are. It's like having a dependable friend. You know they'll always be there when you need them, just like a low coefficient of variation indicates that your measurements are consistently reliable. Think of it this way: if you're baking a cake, you want your measurements to be accurate and reliable. You wouldn't want 1 cup of flour to suddenly become 1.5 cups, right? That's why linearity and coefficient of variation are critical. They ensure that your cake, or in this case your measurements, turn out just right every time. With a clear understanding of linearity and coefficient of variation, we are ready to move on to pre/post-analytical. Next up is the pre/post-analytical phase. Let's dive in. The pre-analytical phase is all about the steps that occur before the actual testing process. This includes everything from sample collection, handling, and preparation to the transport of the sample to the lab. On the other hand, the post-analytical phase involves the steps after the testing, such as interpreting the results, reporting, and archiving. Now, why are these phases so crucial? Well, any error occurring in these stages could significantly impact the accuracy and precision of the test results. For instance, improper handling of a sample during the pre-analytical phase could lead to contamination, thus skewing the results. Similarly, misinterpretation during the post-analytical phase could lead to incorrect conclusions. Therefore, maintaining strict quality control during these phases is key to ensuring reliable and accurate results. Having understood pre/post-analytical, let's move on to the next set of terms. Now, let's explore accuracy, skewness, and confidence limit. Firstly, accuracy. It's a term that's thrown around quite a bit, isn't it? In quality control, accuracy refers to how close a measurement is to its true value. When your measurements are accurate, you can trust them to reflect the real-world situation you're dealing with. Imagine being in a dart game. The closer your dart lands to the bullseye, the more accurate your throw. Next up, skewness. This is a slightly more complex concept. It's a measure of the asymmetry of the probability distribution of a real-valued random variable. In other words, It tells us how much a distribution leans to the left or the right. A distribution with a long tail on the left side, for instance, has a negative skewness. Conversely, a distribution with a long tail on the right side has a positive skewness. The skewness of a distribution can have a significant impact on the mean, median, and mode of a dataset, which in turn affects the quality of the results. Finally, let's talk about confidence limits. These are the bounds within which we expect a particular measurement to fall a certain percentage of the time. For example, if we say we have a 95% confidence limit, it means that we expect our measurement to fall within that range 95 times out of 100. Confidence limits give us a way to quantify the uncertainty in our measurements, which is essential for making informed decisions in quality control. In essence, accuracy, skewness, and confidence limits are all about understanding our data better. They help us assess the quality of our results and make more informed decisions. When we know how accurate our measurements are, how skewed our distribution is, and what our confidence limits are, we can improve the reliability and validity of our work. Now that we've covered these concepts, let's proceed to the next set of terms. Before we dive deeper into our next set of concepts, we'd like to take a brief moment to connect with you, our viewers. If you're finding this video helpful and informative, don't forget to hit that like button. It helps us reach more people and spread the knowledge. Also, share this video with friends, colleagues, or anyone you think could benefit from understanding quality control better. And most importantly, make sure to subscribe to our channel. This way, you won't miss out on any of our upcoming content. We're dedicated to providing you with comprehensive and easy-to-understand information on various topics. Your engagement motivates us to keep producing quality content, so go ahead, like, share, and subscribe. Now let's get back to our exploration of quality control concepts. Our next stop includes precision, mean value, and normal distribution. Let's begin with precision. In the realm of quality control, precision refers to the closeness of two or more measurements to each other. If you were to take multiple readings of the same sample and got similar results each time, you'd say your measurements are precise. It's about consistency and repeatability, really. However, it's important to remember that precision doesn't necessarily guarantee accuracy. You could be consistently off the mark. Now, onto the mean value. This is a statistical term that you might know as the average. It's calculated by adding up all the values in a dataset and then dividing by the number of values. The mean value is a reliable way to represent a dataset with a single number. In quality control, it's frequently used to understand central tendencies in data. Lastly, we delve into the realm of normal distribution. Also known as a bell curve due to its shape, normal distribution is a statistical function that describes all the possible values and likelihoods that a random variable can take within a given range. What makes it particularly noteworthy is that the data around the mean is symmetrical. That means most of the data falls near the mean value, tapering off equally on either side. This symmetry is a critical aspect of many statistical methods and tests. These three terms, precision, mean value, and normal distribution, are the foundation of understanding data quality. Precision tells us about the consistency of our measurements. The mean value gives us the central tendency, a single value that represents our entire data set. And normal distribution helps us understand the spread and likelihood of our data values. With these terms under our belt, we're ready to tackle the final set of terms. Let's now delve into reliability, standard deviation, and standard deviation index, SDI. Starting with reliability, it's the consistency of a measure. An instrument is said to be reliable if it produces the same results under the same conditions over and over again. Moving on to standard deviation, it's a measure that quantifies the amount of variation in a set of data values. In simpler terms, it tells us how much the data deviates from the mean or average. Now, what about the standard deviation index, or SDI? It's a statistical tool that helps us to understand how much a single measurement deviates from the mean. It's calculated by subtracting the group mean from the individual measurement and then dividing by the standard deviation. These terms play a critical role in ensuring the quality of results, helping us to understand variability and to identify trends or shifts in data. Having unraveled these terms, Let's proceed to the last two concepts. Finally, let's decode delta, OD shift, trend, and Levey-Jennings charts. Delta refers to the difference between two measurements, often used to track changes over time or identify sudden shifts in data. OD shift, on the other hand, is a shift in the optical density of an object or solution, typically used to detect changes in the properties of the subject. Now, when we talk about trends, we're referring to the long-term movement of data after removing random fluctuations. It's a great tool to understand the trajectory of your data. Lastly, the Levey-Jennings chart, named after its creators, is a quality control tool used in laboratories. It plots individual control measurements and uses standard deviations to determine if a process is in control. These tools and concepts are vital in monitoring and improving the quality of results, making them indispensable in the world of quality control. With these last terms, we've covered our list of key quality control terminology. Now that we've learned these terms, let's do a quick review. We've traveled through the realm of quality control terminology, starting with linearity and the coefficient of variation. These concepts help us understand how closely our data aligns with a straight line and how much our data varies. We then ventured into the pre- and post-analytical stages, crucial for ensuring the accuracy of our tests. Next, we delved into the intricacies of accuracy, skewness, and confidence limits, followed by an exploration of precision, mean value, and normal distribution. These terms form the backbone of statistical analysis in quality control. We unpacked the notions of reliability, standard deviation, and the standard deviation index, vital for understanding variability and consistency. Lastly, we decoded the mysteries of delta, OD shift, trend, and Levey-Jennings charts, essential tools for monitoring and improving quality. Remember, quality control is paramount in any field, and understanding these terms can greatly enhance your ability to ensure excellence. Until next time, keep learning and exploring. Before we wrap up, we'd like to remind you that your engagement is what fuels our passion to keep creating these informative videos. If you found this video helpful and want to continue learning with us, please do not forget to like, share, and subscribe to our channel. Your support helps us immensely in creating more content like this, and it is greatly appreciated. Remember, the journey towards understanding quality control doesn't end here. Here are some past questions for medical technologist certification examination. A graphical presentation of run-to-run or day-to-day quality control values is a select one. A. Levey-Jennings chart. B. Systematic flow chart. C. Westgard chart. D. Lawson chart. Answer is Levey-Jennings chart. An abrupt demonstrated change in the mean is a select one. A. Shift. B. Trend. C. Variance. D. Deviation. Answer is shift. Qualitative examinations are those that A. Qualify for wave testing. B. Produce non-numerical results. C. Do not require quality control. D. Do not require proficiency testing. Answer is produce non-numerical results. What characteristics, functions do calibrators have? A. They contain a known amount of analyte being tested. B. They monitor the quality of reagents. C. They monitor the quality of the sample. D. They prevent equipment failure. Answer is, they contain a known amount of analyte being tested. Keep exploring, keep questioning, and most importantly, keep learning. Thank you for joining us on this journey, and we'll see you in the next video.